wait for some more time. Dr.
No, sir, we
Majid?
have given time 7 o'clock now. We should wait for 2-3 minutes, sir.
Yeah.
Okay.
Because
Okay.
some of them will join exact time or maybe 1 or 2 minutes late. I will check whether it is coming exactly or not.
Okay.
Can you see, sir, the slide, full slide?
No, the slide.
You can see the slide, sir?
No, the slide is not visible now.
Okay, sir.
Sir, now we can start. Sir, introduction and the Atal.
Right. But maybe if we can see if you can put on your first introduction or first slide and see
Okay,
if
sir,
everything is
I will
fine.
see that.
Yeah.
Can you see the slide now, sir?
No, the slide is not visible. No.
Okay, I will see that. I'm not getting share mode actually.
At the bottom you present.
No, present is there. Once I'm clicking on present,
Okay.
then entire screen I'm giving best of video and animation. Yeah. And
Then you need to select the screen first.
Maybe you can select a specific window, not the entire screen.
okay, sir, I will select. The share option is coming disabled, sir, actually in my that.
Share
What is the problem? Share option is coming disabled from this side. It should be licensed one, sir, software.
No. This is the Google Meet that we are
Google
using.
Meet is free now.
Yes. Yesterday we had the presentation. It was working fine. The same scheme we followed.
Then why I'm not getting? We'll go present, then let me see tab.
You can leave the meeting, then rejoin. Maybe.
Okay, sir. I will see that. I will
Just
leave
the
and
meeting,
again I
then
will join.
rejoin.
Okay, sir.
Is that up arrow visible to you, sir? No, you are mute. You are mute, sir.
It is not coming enabled actually. I don't know what is the problem.
Okay, so what we can do is, I can start the slides. I think you have shared with us. So let me download and start, and you can start let me just download those slides.
I will share once again. I will mail to you. Wajid, that you download. Oh, that
Yeah, please send me the email. I will.
Immediately I'll send the email. Okay, 1 or 2 modification I've done. Okay.
Yeah. Please share. Please send me.
Okay. In the meantime, while this sharing and all those things are taking place, I'll try to introduce today's speaker to all the participants. First of all, I would like to welcome to the second day of the Atal FDP program. And we have got now a speaker, Professor Mahesh Chandra. He is from the School of Electronics and Communication Engineering, Reva University, Bangalore. He actually did his AMIE from IEI Kolkata in 1994, MTech from JNTU Hyderabad in 2000, and PhD from AMU Aligarh in 2008. He had worked as the head of the Department for Electronics and Communication Engineering at SRMS College of Engineering and Technology, Bareilly from 2002 to 2005. He has also worked as professor from July 2005 to January 2020 in Electronics and Communication Engineering Department, Birla Institute of Technology, Misra, Ranchi. He was also Dean Students Welfare at BITS, Misra, Ranchi. Currently, he is working as a professor in the School of Electronics and Communication Engineering, Reva University, Bangalore. He is active in research and he has published more than 200 research papers in journal and international conferences. He has guided 18 PhD students, 29 MTech dissertations, and more than 50 BE projects. His area of interest is feature selection from audio signal processing, human computer interface, and machine learning. So he is a very relevant person for this FDP program, and I am sure that you will be benefited from his experience that he has. He has actually delivered a lot of keynote addresses at national and international levels, and has completed one consortium project in 2018 from the Ministry of Electronics and Information Technology on speech-based assess of agricultural commodity price and weather information in 12 Indian languages dialect. So different languages, dialects that are important. So he has worked upon that. He has organized various conferences and international conferences and short-term courses as well. He has visited abroad, China and Singapore, related to the conference work. Number of noise canceller, then another best paper award in 14 in the conference in a unique low complexity parameter independent adaptive design for eco reduction. He has got in 15 again a Best Paper Award in Performance Evaluation of Artificial Neural Network for Isolated Hindi Digit Recognition with LPC and MFCC. MFCC, we had discussion yesterday about that. He was actually honored as a Best Alumni Award of 2017 at IEI headquarters of IEI in on 17th December 2017. So he has got a vast experience in the domain of speech signal processing, and today he will be talking about techniques for speech processing and its application in automation. So as he has pointed out that initially he will talk about the basics of that algorithm, and then real-time implementation, real application he will take up in the next part. That is the second half of the lecture. So I would request you all to be attentive and try to absorb as much information as he is giving, and we will have questions, as we have decided that after the 50-minute slot, you can type the questions in the chat box, and then that will be discussed during the break, 10 minutes break that we will be having before the next talk. I would also like to thank the AICT Atal FDP program for giving us the opportunity to organize this short-term course of 2 weeks in the offline and the online mode, and I hope that this will be beneficial for the participants as well as to us also. So with this word, I would give the floor to Professor Mahesh Chandra. Please go ahead.
Thank you, sir, for introduction and for inviting me for this FDP. Can you see my slide now?
Yes, sir, it is visible to us.
Okay, sir. So now our today's topic is techniques for speech processing and its applications in automation. Presently, I am working at Reva University, Bangalore, and this is under speech-enabled automation technologies at Electronics Engineering Department, AMU Aligarh. In this talk, first you will have the introduction related with this automation. Then you will have what is automatic speech recognition. Then we have hidden Markov model. Under hidden Markov model, we have hidden Markov chain. Then what is hidden? Why it is known as hidden Markov model? Then we have elements of HMM. In elements of HMM, we will see state transition matrix A. We will see the initial state probabilities pi, and then we will see the observation symbol probability. Then that HMM model contains 3 parameters: A, B, and pi, A, P, and lambda. That then discrete time Markov process. What is discrete time Markov process? I will explain that with the help of an Weather model. Then discrete hidden Markov model, we will go with.
Sir, I think screen is not changing. You might be changing some slides.
Correct, I will change. I am on the second screen outline only. Then I will change. Okay.
Yeah,
then
actually, presently it is on the first slide actually.
Earn and wall model. I am giving just the outline first. Then I will go to next screen.
Okay.
Then we have 3 problems of HMM and their solutions. Especially first problem, we use forward and backward algorithm, and why we use these algorithms for the solution of first problem of HMM. Then second problem, that is optimal path sequence, we will use Viterbi algorithm, and third problem is maximization probability of observation for a given model, lambda Wambach algorithm. Then how HMM is used in automatic speech recognition system. After that, you will see types of HMMs. Then I will explain isolated word recognition system using HMM, and then at the end references. Now the slides have changed.
No, sir, not changed.
Slides are not changing.
No, no.
No,
We are on the very first slide.
I am at slide number
Press
3 now.
F5. Sir, press F5.
Okay, wait.
You may click on the. Actually, it is not changing here.
Wait, I will see that.
Yeah, now it's changing. Yeah.
Now it's
your-
changing? Okay.
Yeah, slide number 7. You are right now on the slide number 7.
Okay. I will go back and
Yes, changing.
now it is changing. Is it
Yes.
visible to all of you?
Is it visible to others?
Yes, it is visible now.
Okay. So this outlines part I've already explained. What are the main contents I'm going to explain today? Now I'll go to introduction. As our topic is speech-enabled automation technologies. So first, let us see what is speech-enabled automation technologies. Automation, in simple words, you can say it will reduce the human intervention in different aspects. Now, for example, virtual assistants like Alexa, Cortana, Google Assistant, or Siri works on speech recognition and conversational artificial intelligence concepts. Voice-controlled wireless home automation. Lot of the students, lot of the researchers are working in this field, that they develop speech-enabled in integration with IoT device, which makes the life easy for the elderly and disabled people. They can easily control home utilities fully based on phone through voice commands. Suppose that in a home, they have 3 rooms, there are 3 fans, 3 AC, fridge, cooler, or lights. By giving the voice-based commands, they can put them on and put them off. That means they can integrate it, speech signal with IoT devices, and the system can be developed like that, and these are available in day-to-day life. Then voice search. This voice search is arguably the most common use of voice recognition. Reportedly, in 2022, in US alone, millions of users would have used a digital assistant at least once a month. Moreover, according to a PwC PricewaterhouseCoopers survey, using a voice assistant to search for something by the preferred method of 71% of participants in US. The next application of the voice is speech to text. Suppose that I am giving the lecture. My speech will be automatically converted into text. The systems are available. So voice recognition enables hands-free computing. Its use cases include, but are not limited to, writing emails, composing a document on Google Docs, automatic closed captioning with speech recognition, for example, YouTube, automatic translation and sending text, and many more applications are available for this. Voice commands to smart home devices. Just now I've told you that smart home devices use voice recognition technology to carry out household tasks such as turning on the lights, boiling water, adjusting thermostat, and more. Some statistics of smart home devices are: good number of voice assistant users state smart home devices as their primary regions for investing in an Amazon Echo or Google Home. An accurate voice recognition system requires a diverse audio data set. Now this line, the last point, an accurate voice recognition system requires a diverse audio data set. I'll just elaborate this point. Suppose that in a family, we have 4 members and 10 devices have to be operated with the speech signal. So that you are using fan on, fan off, light on, light off. Then for 4 persons, if you take less number of samples in noise-free environment, then the system may work perfectly all right. But if in place of 4 persons, the persons becomes 100, and that to be from different states of India. Let us see, 3 persons from one state, 4 persons from one state, like that there are 100 users. Now here, the speech signal or speech commands which will be used by them for operating these lighting system, lights, fans, fridge or geyser, will have different accent. They will vary from person to person. That means variability in the signal has come. So the system efficiency will go down if we use limited data set. So what I want to tell, if you want to work and design a system that is robust free and anyone can use, you need huge data set for training purpose. I will explain this training and testing. Once you'll go for automatic speech recognition system. Another diversity may come that a person may be speaking and at the same time some other sound may be coming, such that you have a dog in the home. Dog will start barking and you will give the command the fan to be on. It may not work perfectly. So all these things can be taken into account and further the improvements can be done in the present research. Voice recognition is also used in customer service. Voice recognition is an important AI application in customer service. Voice recognition is an effective call center service solution available 24/7 and is cheaper than live replies. The common use cases of speech recognition in customer service are interactive voice response system. It is one of the oldest speech recognition applications and allows customers to reach the right agents or resolve their problems by voice commands. Then analytics. Transcription of thousands of phone calls between customers and agents help identify common call patterns and issues. That means they will have a large, huge database of the different calls from different people, and they will identify the common call patterns. What is the requirement of the customers? What are the basic requirements of the customers? That can be, the analysis can be done with the help of speech signals. Pre-sales. Sales development resources calls can be wasteful. An example would be insurance companies calling their leads and asking them questions. Suppose that they want to advertise for a policy, then they are required to explain each and every point to their customers. But with voice recognition system, they can have the basic parameters, 10 to 15 questions. Automatically those questions will be asked and the customer will keep on replying. So the process becomes easy for the company as well as for the client. Okay, the benefit is that the caller will not have to wait to be connected with the sales representative. Rather, the bot will immediately start the evaluation and qualification process. Then voice biometrics for security purpose. Similar to how your smartphone allows you to unlock it with your voice, with your fingerprints. Even all Android phones are having, or most of them have, you can operate the speech signal. Vocal biometrics uses a person's speech to authenticate them. Users might be required to say their name aloud during logins rather than typing a password. Alternatively, speech biometrics can be used in fintech to authorize transactions and to guarantee they are genuine and consented from the account owner. Now here, I would like to mention one more thing. Suppose that my phone is voice operated. Lock will open if I tell my name Mahesh. And I can operate my mobile. But in case of me, if somebody else tells Mahesh, then as per normal public, the mobile should open. But no, mobile should not get unlocked if somebody else tells Mahesh. If I tells Mahesh, then only it should get unlocked. That means, along with the recognition of the name Mahesh, it will also do the verification of the speaker, whether it is the correct speaker to whom the mobile phone belongs or it is different person. So here two processes will take place. One is the speech recognition, another is speaker verification. When both are satisfied, then only the mobile gets unlocked. So what we can say, alternatively, speech biometrics can be used in fintech to authorize transactions and to guarantee they are genuine and consented from the account owner. Besides, speech biometrics can restrict access to authorized personnel in healthcare, while maintaining patient confidentiality is very, very important. Then we can use the application of speech and automotives. In car, speech recognition system have become a standard feature for most modern vehicles. Research has shown that by 2025, most of the drivers will use an in-car voice assistant. That means they can select their choice song by using the voice signal. They can select the driver can concentrate in the front and wheels on the hands on the wheels properly, and with the help of voice signals, he can control many things inside the car. Out of that, some applications are initiating phone calls, selecting radio stations, setting up directions, or playing music. These all can be controlled with a speech signal in cars. Next application of the speech signal in academics. 80% of sighted children learning is through vision, and their primary motivator is to explore the environment around them. Speech recognition can create an equitable learning platform for children with no or low sight. Suppose that they are not able to see, they have low sight, then they can learn with the process of audio signal or the speech signal. Language learning tools such as Duolingo use speech recognition to evaluate users' language pronunciation. Pronunciation evaluation is a practical computer-aided language learning application. This software is available. By using this software, you can improve your pronunciation and some other basic parameters. And we can use the speech signal in media and marketing. Speech recognition tools such as dictation software can enable people to write more words in less time. In healthcare, during patient examinations, doctors need not take notes of patient symptoms. Medical transcription software use speech recognition to capture patient diagnosis, notes, and saves doctor's time. That means doctor will keep on telling, and automatically it is converted in the form of text. By that, doctor need not to write. Prescription can be given at a faster time, and the doctor's time will be saved in that. He can see the more patients. Then speech signal can also be used to check the state of the mind. That means whether the person is depressed or whether the person is normal. That states can also be checked by taking some audio files from a particular person. Depression speech recognition technology listens to a patient's voice to identify the existence or lack thereof of depression undertones through words such as unhappy, overwhelmed, bored, feeling, void, and so on. That means there is one field in speech recognition or under audio signal processing that is called emotion recognitions. Means from the text itself, you can detect the emotions of a person, whether the person is happy, whether the person is sad, where the person mind is not working properly, where the person is neutral. There are many types of emotions. So it can be used to test the mental state of a person. Next is vendors such as Sonde Health have created mobile applications that gives user a score for mental fitness based on their voice, tone, use of words, energy, fluctuations, and rhythm, among other variables. So these are some of the applications where the speech signal can be used. There are many more applications nowadays, and many more will be developed in coming years. Now, in all these applications, the basic concept of automatic speech recognition is used. Not exactly, but almost all automatic speech recognition system concept is basically used in all these systems. Now let us see what are the applications which use the concept of ASR. For any automatic speech recognition system, basically three things are required: corpus or database, feature extraction, and classification. Now, corpus or database may be small, such as we have a small database of 10 speakers for 10 Hindi digits. We can have a database of 100 speakers for 100 sentences. The databases can be used in different applications, but for automatic speech recognition, the huge database is required. And in our project, which I have completed a consortium project, in that the database was prepared by 12 institutes all over India. I was from BIT Mesra, and some of the students from many IITs were involved in that, and 2-3 more private institutes were there. Once you have proper database, then after that, you have to go for feature extraction. Now, in feature extraction, basically two techniques emerged. In 1970, it was LPC, and 1980, it was MFCC. LPC means linear predictive coding. It is nothing but the prediction of a speech signal with linear combination of past few samples. That is LPC. And this technique depends on speech production mechanism of a human being. How we are able to produce the speech. The human organs have been modeled into mathematical concept, and then this linear predictive coding came into existence. Then second technique, the basic technique, we have MFCC, male frequency statistical coefficients. This technique of feature extraction depends on human perception, how we are able to hear the sound. So these two techniques depends on two basic fundamentals of human speech production, that is LPC, human speech perception, that is MFCC. There are many people have worked on feature extraction techniques with combination of these two, with advancement of these two. Basically, the Fourier transform was used. Then we have gone for some other transform, Dirichlet transform, other transform we have used for exploiting the speech signal and extracting the useful information which can perform better for normal speech in presence of noise, or for all vowels, phonemes, and so on. Anyway, this is not the topic today, but I've given very simple example of the feature extraction. Now, once you have calculated the feature extraction, then we have to train the system and then test the system. This is done with the help of classification techniques. There are many classification techniques like logistic regression, naive-Bayes classifier, k-nearest neighbors, decision tree, support vector machine, hidden Markov model HMM, and GMM. Today, we will discuss our hidden Markov model here in this topic. That what is hidden Markov model, how it can be used as a classifier. Okay. Now here, there are two phases. One is training, another testing. Let us take one small example. What is the meaning of training? In one family, let us take an example of Aligarh. One child takes birth in a family. Then he is not going to school. He becomes 3 months, 4 months, 6 months. He keep on listening the words or the language spoken by the family members, by the father, mother, or brother. Then automatically the child, after 5 months or 6 months or 7 months, he starts speaking few words. That means the training of the children had taken place through the family members, and he automatically starts learning the basic language spoken in his home. And after that, he becomes little more familiar with basic words. Then the family members will ask, Papa bolo, tell me father, tell me mother. The child used to speak those words. That is called testing. In the similar fashion, for development of an automatic speech recognition system, first the system should be trained and then it should be tested. So there are two phases, one is training phase and the testing phase. So here in this topic, I will talk elaborately on hidden Markov model. It is a statistical model. Now, this is speech recognition architecture. I will elaborate this at the end, but the basic functions I will tell here, which I have already explained just now. Here, we have shown the speech waveform. After that, we have divided that into small segments. Then, after speech signal, we have calculated the feature extraction. That means we have extracted the features from the speech signal. Then those speech signals, features, either it is stored offline or it can be used online for automatic speech recognition system. Then we use the classification or recognition, as we are going to explain HMM, which is a classification technique. By using any classification technique, we may go for recognition of phonemes, and then we may go for recognition of words. Any word is a combination of some basic phonemes in a language. Every language will have different set of phonemes. Hindi will have different set of phonemes. Urdu will have different set of phonemes. Tamil will have different set of phonemes. Some basic phonemes are similar from one language to another language, but some of the phonemes will vary from one language to another language. So, speech signal, extraction of features, then training and testing the terms under classification, then phonemes will be recognized. And after that, we can go for recognition. Now let us start our topic, hidden Markov model. Now let us see, this hidden Markov model is a probabilistic pattern matching technique in which the observations are considered to be the output of a stochastic process and consist of an underlying Markov chain. So first you will see what is the meaning of Markov chain. A Markov chain is a random process with the property that the next state depends only on the current state. Okay, we will explain in the next few slides what the meaning of state. That means Markov chain will follow a principle that the next state will depend only on the current state. This assumption we use here. In the speech recognition, the observed data is the acoustic signal and the words are the hidden parameters. Okay, so what is the observed data? Is the acoustic signal what is available with us. And when we have to identify the words in that particular language, that becomes the hidden parameters. In a hidden Markov model, basically there are three problems. First problem is how to find out probability of an observation sequence for a given lambda. For this, we have direct solution, then we have forward and backward algorithms for the solution of problem 1. That means how to calculate probability for the observation sequence when lambda is given. Then problem 2 is optimal state sequence. We will use here, today I will explain Viterbi algorithm and why we use Viterbi algorithm. Optimal state sequence, I will take very practical example I will tell. Suppose that one of the participants has come from Calcutta and he attending short-term course at Aligarh Muslim University, Aligarh for 15 days. After 15 days, he wants to go to Calcutta back. He has different options. He can take directly Rajdhani train from Aligarh railway station. He can reach to Howrah. He can go to Delhi. He can take another train from Delhi. Then he can reach to Calcutta. He can take flight from Agra. Then he go to by Delhi by flight. From Delhi, he can take flight for Howrah. That person can take a flight to Bangalore, and he can take the flight for Kolkata. A person can take train from there to Nagpur, and he can take another train from Nagpur to Howrah. The various paths are available for that person to travel from Aligarh to Kolkata. But here we have to see, in some sense, that which is optimum path for that person to reach to Kolkata. Here we can take parameters such as time, the cost, and some other parameters can be considered. So we have to minimize the time, we have to minimize the expenditure, and the person must reach in Calcutta. Similarly, so there will be the best sequence, as we can roughly say that if the person takes train from Aligarh junction, then he can reach directly to Kolkata. That may be an optimal path sequence. Similarly, we will see in hidden Markov model that how to find out optimal state sequence. For this, I will solve forward and Viterbi algorithm with the help of an example in the second session. Then we go to problem number 3. In the first problem, we have find out the probability of observation sequence for a given lambda. Second problem, we have gone for optimal state sequence selection. Third is maximization of probability for observation sequence for a given lambda. Okay, that means the probability of which state, which path is highest, we should follow that path in terms of that some parameters. Now we'll see those what are the parameters in hidden Markov model. In hidden Markov model, the basic elements which are used. One basic element is n, capital N, that is called number of states. Before that, I'll go to one slide and then I'll come to this slide. You see this discrete hidden Markov model. This is called Arn and Wall model. Here, Arn1, Arn2, and so on, there are n arms. Every arn have 6 different colored walls. That means red, green, blue, black, purple, and yellow. Now, in Arn1, probability of red walls is 15%, probability of green walls is 42%, probability of blue is 13%. This complete probability should not go more than 100%. That means probability cannot be more than 1. Now here, what is the meaning of states? States means how many urns are available in the experiment. Here, in the experiment, we have total number of n urns. So that is called the state. Now, what are the observations? Here, when we draw a ball from the urn, that color of the ball will be recorded. So that becomes first observation, that may be blue or black. Then that will be replaced back, another ball will be drawn. It depends on how many times you want to draw the ball. 3 times or 4 times or 5 times. That will become observation sequence. So these are the symbols, that means the colors, and the probability of those colors will be called the symbol probability. Now I'll go to this slide. So you understood what that means, number of states. So Arn and Wall model, we have n states, S1, S2, S3, and Sn. We have capital M, number of observation symbols, V1, V2, V3, and Bm. Here in that Arn and Wall model, we have 6 observation symbols. That means 6 different colored balls are available. Red, blue, green, purple, yellow, orange, like that. There are only 6 colors. So number of observation symbols becomes 6. That is V1, V2, V3. It will go up to 6 in that Arn and Wall model. And number of states are n, capital N. Then we go for next parameter, that is state transition probability, that is denoted by capital A. And so combination of different state transition probability in the form of matrix is denoted by capital A. So capital A is a matrix. It depends on number of states available in the example. Then observation symbol probability, that means B is equal to Vjk. So J is state, that means 1 to n. In Arn and Wall model, we have n states. We may be in state number 1 if J is 1. We may be J is equal to 5, we may be 5th state. J may be n, we may be nth state. K is the color of the ball. So if it is B1, 1, that means 1 is the state and K is 1, that is denoted to the red color. So that means in state 1, red color probability will become Bjk. If we take J is equal to 3 and K is equal to 3, so that becomes state 3, the probability of that ball for third color, let me say that is black color. That will become the symbol probability for the black color in state 3. We will see that state diagram, that will be more clear. Another parameter we have initial state distribution, that is denoted by pi. Now how many states are there? That many probability will be there, or that many values will be there. If 2 states, we'll have 2. If 3 states, we'll have 3. Then capital T, the number of observations of sequence. How many observations are available in the sequence? O is equal to O1, O2, O3, and OT. Then HMM is completely characterized by lambda is equal to A, B, pi. So what is A here? A is state transition matrix. You can see here. B is symbol probability matrix available here, or sometimes it's called emission probabilities I will explain in the second session one example, a numerical example. Then the things will become very, very clear and very easy. Pi is the initial state probability. So these three parameters initially will calculate A, V, and pi. So these are the elements of hidden Markov model. Now I will go to one discrete time Markov process, that is Bether model we are taking here. Here there are three states. It is well-known example and it is given in Fundamentals of Speech Recognition by Ravener and Jung, this model, and in many papers also this example has been explained. It is easy to understand. So with the help of this example, I will explain what is the meaning of state diagram. State 1 here is rain. State 2 is cloudy. State 3 is sunny. Now here you see that we can go from any state to any state and the values are written on that path. Suppose that this is your rain, state 1. Next day, the model remains in the same state. That means the probability of that today rain, tomorrow also it will be rain, it is 0.4. Or you can say 40%. Then suppose that today rain, tomorrow it go to cloudy. So this probability is 0.3, that is 30%. Then today rain, tomorrow it may be sunny. So from rain, the state transition can take place to sunny. So the value is 0.3, that is 30%. Here, one thing is to be noted that all outgoing probabilities should not be more than 1. Or if you calculate in terms of percentage, not be more than 100. That means rain will remain rain tomorrow, 0.4. It will go to cloudy, 0.3. It will go to sunny, 0.3. We add this 0.4 plus 0.3 plus 0.3, or you add here in this line, 0.4 plus 0.3 plus 0.3, it becomes 1. Similarly, you can see at cloudy, state number 2. Here also, the addition of all these probabilities will be 1. 0.2, 0.6 plus 0.2. Sunny also, the addition of all these probabilities will be equal to 1. So that is the basic principle of fundamentals of probability theory, that probability cannot be more, or the addition of all outgoing probability here should not be more than 1. Here in this example, the initial state probabilities we have taken as 1, 1, 1. For all the states, the initial state probabilities are 1. That is, equal chances are there. It may be different in examples. Now, so in this Bether model, we have total 3 states. One is rain, another is cloudy, another is sunny. Here we can go from any model to any model. Now you see the state transition matrix. Once the model goes from, let us see, this is state 1. If it remains in state 1, that will denote by small a 1, 1. 1, 1 means it was in state 1. It remains in state 1. The probability of that is 0.4. Suppose that today our model, or today it is rainy, tomorrow it will be cloudy. Then it is going from rain to cloud. The probability of that is 0.3, this side, top side. So that will be A12. So that is transition matrix when the transition takes place from state 1 to state 2. Like that, all possible transition probabilities are given here. State transition probabilities. So state transition probabilities for this state is 0.3, that is A12. Here from 2 to 3, it is A23, 0.2. From 3 to 2, that is A32 is 0.1. Like this, different transition probabilities which are given in this matrix. Now, one example is there. What is the probability that the weather of 8 consecutive days is sunny, 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 rainy, rainy, sunny, cloudy, and sunny? That means we have to find out the probability of the observation sequence. The observation sequence is sunny, 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 rainy, rainy, sunny, cloudy, and sunny for a given model. What is the meaning of model? Model means the transition matrix is given to us, and initial state probability are also given to us. Okay. Model means A, V, and pi. Lambda is A, V, and pi. Now here, so probability of observing sequence for model. Now here the sun is state 3. So 3, 3, 3, 1, 1, 3, 2, 3. So let us see this. Initially, the system is starting from state number 3. So that will take probability of 3. Initial state probability of state 3, and that is given 1. Then after that, it goes from 3 to 3. That means next day also sunny. So the state transition probability, when it was sunny, it further remains in sunny. So that means 3 to 3, 0.8. Next again, it was sunny, it remains in sunny, 0.8. Now here you see this point. Here, today it is sunny, tomorrow it will go to state number 1, that is rainy. That means from here we are going to state number 3, we are going to state number 1, the value is 0.1, we are taking 0.1. Then 3, 1, it was in rainy, then again it goes to sunny, 0.4. Like this, all properties are multiplied together, and the value we are getting 1.536 into 10 to the power minus 4. That means this is the probability that the weather for 8 consecutive days will remain in this observation as per the observation sequence. So this is one example, state and weather model. Anybody have any doubt here? You can ask any question about weather, or at the end of this session you can ask, no problem. I'll go to next slide now. Now, we have taken discrete hidden Markov model that is called urn and wall model. In this, there are n urns. Every urn has combination of 6 different walls. That is red wall, green wall, blue wall, black, purple, and yellow. And as per depending on number of balls, the probability is calculated. All of you know the formula of probability. The probability P is number of chances in favor divided by total number of chances. So to get 15% for red here, 15% balls are red out of 100. We can see. So 15 by 100. So that is 15% here. 42% balls are green. So probability of the green ball will be 42 by 100. 42%. Probability of blue will be 13%. 13 by 100. Probability of black is 7%. So 7 divided by 100. Probability of purple is 11%. Probability of yellow is 12%. Like this, probability of all different colors in different urns are mentioned here. Now let us see little elaboration of this urn and wall model. We are assuming there are n glass urns in the room. In room, n glass urns are available. Each urn contains colored balls of m is equal to 6. What are the 6 colors? That is red, blue, yellow, purple, and black, and green. Different colors. Now a person, the curtain is put in front of the gate, and a person who wants to perform the experiment he cannot see the urns. That means randomly he is asked to select any urn. He'll put his hand inside the curtain, randomly any one of the urn will be selected. Then he pick up one wall and he bring out the wall outside. Then you will see the color of the ball. And that becomes observation number 1. So color of the ball will be recorded. Then that ball will be replaced back in the same urn. He will repeat the experiment. Again, randomly he will select any of the urn, and he will select any ball randomly from that urn. And then again the color of the ball will be recorded. So like this becomes observation sequence. So let us see, he is performing this experiment 5 times or 6 times or 7 times. Only the color of the walls are available as an observation sequence. What is hidden here? Now we are talking about hidden Markov model. So what is hidden? Here hidden is which urn is selected. Whether it is 5th urn or whether it is 7th urn or whether it is 10th urn. So that is the hidden. So this step is called the hidden. So the entire process is going on for some time and generates finite. I will just go through this. A person in a room is asked to choose randomly an initial urn. From that urn, the person randomly selects a ball and its color is recorded as the observation. The ball is replaced back in that urn. The person is again asked to choose a new urn randomly. And the ball selection and observation process is repeated. The entire process is going on for some time. Then after certain observation, he stops the process. Okay, the observation has been recorded. This is called urn and wall model. So here, you should have been clear now with parameters of HMM model. That means first is the state transition probability, capital A. Second is symbol observation probability, that is the observation of colors. Third is states. So here in these examples, we have taken n states. There are n urns. M is 6. That is number of different colors are 6. That becomes 6. Okay. Now we'll go to HMM problem and solutions. So here, there are 3 basic problems in HMM. The first problem is, given the observation sequence O, that is O1, O2, OT, and a model lambda. What is lambda? Just now we assume lambda is a combination of 3 parameters, that is state transition matrix A, observation symbol probability, that is B, and initial state probability, that is pi. How do we efficiently compute probability of this observation when the model lambda is given to us? This A, B, and pi is given to us. We have to find out the probability of the observation sequence. This is the problem number 1. In this problem number 1, we have direct solution, then we have forward algorithm, then we have backward algorithms. In direct solution, we have state sequence. So state sequence, we are represented here by Q, Q1, Q2, Q3, Qt. So there are total number of states are capital T. Total possible state sequence will be n to the power t, because there are total n states. There are total n states. Recollect, remember the urn and wall example. We have n urns and we have created t state sequences. The total number of possible state sequence becomes n to the power t. Then I'll make it clear. Then we'll go on a numerical example in the second session. Then we'll assume independent observation O, that is O1, O2, and OT. That means the observation number 2 does not depend on observation number 1. As we have replaced the wall, first wall drawn, we are replacing the same arm. Then we go for second wall. So drawing of the first wall is not impacting the drawing of the second wall. So that means observations are independent of each other and model lambda. Then joint probability of O and Q, that is observation sequence and the state sequence Q. Probability that O and Q occurs simultaneously is given by probability of, you can understand, you remove this lambda, then you can understand probability of A comma B is equal to, or probability of O comma Q when given lambda is equal to probability of observation sequence for a Q and lambda, then probability of Q for a given lambda. Q is the state sequence, O is the observation sequence. Here the concept of Bayes theorem is used. The probability of observation sequence O given the state sequence can be calculated by using this formula. So probability of given observation sequence when the state sequence is given Q and lambda is available is the product of different probabilities. That is T is equal to 1 to capital T. Capital T is the total number of states, transitions, states, total number of, capital T we have cleared here. Capital T is the total number of state sequence, that is the state sequence, Q1, Q2 and Qt. Now here this is probability of OT when state sequence Qt for a given lambda. It is multiplication of, let us see, BQ1 O1. Let's understand this one. This Q1 indicates first state and O1 is the first observation. So this is the symbol probability from first state and first observation. Then the system has gone to second state. So symbol probability for state Qt and observation 2. It will go like this. Then the last one is the observation symbol probability for Qt state. This is the state number and the symbol number is OT, O1, O2 and OT. Okay. If there are total 5 observations we are performing, then it will be 1, it will be 2 and it will be 5. And there are only total, let us see, 5 states only. Then this is 1, 2 and 3 and 4 up to 5. It will go like that. So probability of state sequence from the model is probability of Q by lambda pi Q1, initial state probability of the first state, multiplied by the state transition probability A Q1 Q2. That means the transition is taking place from state Q1 to state Q2. So initially we have started from state Q1, then transition is taking place from Q1 to Q2, state transition matrix A Q1 Q2. Then again transition took place from state 2 to state 3. So state transition probability of Q2 to Q3. At the end, it is state transition probability of Qt minus 1 to Qt. So finally, in direct solution, if we find out probability of O comma Q for a given lambda, it is multiplication of those two equations. That means we'll multiply both the equations explained in the last slide. Pi Q1, initial state probability for state Q1, state transition probability when the system goes from state Q1 to Q2, state transition probability when the system goes from Q2 to Q3, like this. And this is the observation sequence probability in different states. So overall I can say like this: the system is starting from pi Q1 first, then transition is taking place from state Q1 to Q2, A Q1 Q2. Forget other terms. Then in that Q2 Q1, what was the probability of observation sequence? BQ1 O1 multiplied here. Okay. Then we can separate the terms like that. Now, in this direct solution, the computational complexity is 2t n to the power t. N is the number of states, t is the total number of observations or state sequence that we have followed. The computational complexity 2t n to the power t when you go for direct solution of the problem number 1. And this computational complexity is very, very high. To overcome this computational complexity, we can use the concept of forward algorithms and backward algorithms for the solution of problem number 1. So here comes out to be forward algorithm. In forward algorithms, we will define the auxiliary forward variable alpha, that the alpha ti is equal to probability of O1, O2 and OT. Then the system is in state I, Qt is I. Now what is the meaning of this? Alpha ti, it is called forward variable alpha, and alpha ti is defined as probability of the observation sequence O1, O2, O3 up to OT. And at time t, the state sequence Qt is I. That is, the system is in state I at time t for a given lambda. Okay? Lambda means basic HMM, rough model is given to you. Let us understand like this. What is lambda? Lambda contains 3 parameters, A, B and pi. So once again I'll tell, here in the forward algorithm, we'll define the forward variable alpha, Ti, which is nothing but this is the probability of the observation sequence O1, O2, O3 and OT. When the system is in state I at time t. So this is the probability of the observation sequence O1, O2, OT. When the system is in state I at time t for a given model lambda. So what is alpha ti is called? Alpha ti is the probability of observing a partial sequence of observations O1, O2 and OT. We are not observing complete. Partial sequence of observations we are considering here in the form of alpha ti, O1, O2 and OT, such that at time t, state Qt is I. Now, here we use the recursive algorithm in the forward algorithm. First point is initialization. In initialization, we'll consider forward variable as alpha 1i. Now, alpha 1i is pi I. All of you know what is pi I? This is the initial state probability of ith state. Okay. Bi in ith state but by the symbol observed, that is O1. Okay. Now here, then you'll go for induction. You'll go for alpha t plus 1j. That means the system is going from state I to state j. So here alpha t plus 1j is summation of I equal to 1 to n. That means there are total n states we are considering. It will go one by one in all the states. Alpha ti aij is the state transition matrix. So alpha ti is the forward variable multiplied by the state transition matrix aij multiplied by the symbol probability in that state. So there are 3 things. First is forward variable multiplied by state transition probability multiplied by observation sequence. And this summation will take from I equal to 1 to n. That means here in the forward algorithm, we will take the addition. This concept is very clear. I will take one small example in second module. How we do the summation here in that 2 states. How do we calculate this alpha 1i? How we calculate alpha t plus 1j? Then termination at the end, the probability of the observation sequence for a given lambda is nothing but summation from I equal to n alpha ti. Here in this case, The complexity is order of n square t. That means n square in t. So if we take n equal to, let us take 2, t is equal to 5. So it becomes 2 to the power 2, 4 plus 5, 20. If we go direct solution for 2 and 5, here t is 5, so 10, then 2 to the power t, 2 to the power 5. 2 to 5 will be 32 plus 10, 320. So here the total number of calculation becomes 320. We take 2 and 5 value, and here it becomes only 20. So you see 320 and 20. We have taken a small value. Then in computational complexity, this is the difference. If the value of the states and the observation symbols, observation sequence is high, then the computational complexity in the direct solution is very, very high. That's why we should always prefer to use forward algorithm or backward algorithm. Now, after this forward algorithm, this is the forward procedure. We told how the system goes from alpha ti to alpha t plus 1j. This means this is the sj. This is s1, s2, s3, and so on sn. There are total n states. Now, from any state, it can go to sj. So this is a1j. That means it is going from state 1 to state j. State transition probability a1j and goes from state 1 to state j. Here it is going from s2 to sj. So state transition probability a to j, going from state 2 to state j. This is sn, from nth state going to state j, sj. So here it is a and j. So that's why alpha t plus 1 into j will be a combination, summation of all these probability and multiplication by the alpha ti initial. That's what we have done here in the second step here. Alpha ti, aij, bjot plus 1. Bjot plus 1 means symbol, observation symbol probability in that state. That will also be multiplied here. So second algorithm for the solution of first problem is backward algorithm. In the backward algorithm, we define a backward variable beta. In the forward algorithm, we have defined a forward variable alpha. In the forward algorithm, we start from start up to some value in between. In backward algorithm, we start from in between. You see here the observations are from OT plus 1, OT plus 2, and so on O capital T. And forward variable, we were starting from O1, O2 up to OT. Correct? So after OT plus 1, we are defined as backward variable beta ti. So this is OT1, OT plus 1, OT plus 2, and so on, observation capital T. When QT, when the system is in state I and the model lambda is given. So what is beta ti? The probability of partial observation sequence from t plus 1 to n given a state qt is equal to I at time t and model lambda. So system is in state I at time t and model lambda is given. Here all the solution of all problems, one thing is very, very common, that is model is always given. The meaning of model is always given means the lambda is state transition matrix, then symbol probability, observation symbol probability, and the initial state probabilities are already given to you. Here in recursive, then again we use the recursive algorithm like forward algorithm. First we'll do initialization. Beta t I is equal to 1. Here we'll take I is varying from 1 to n. Induction beta t I is equal to j is equal to 1 to n. Here beta t plus 1 into j, aij, bj, ot plus 1. That means this is backward variable, this is state transition probability, and this is symbol probability. Similar to forward variable. Forward variable up to first half, backward variable in second half. You can think like that. Termination, we want probability of the observation sequence for a given lambda. So I equal to 1 to 1, beta 1 I. T will vary from T minus 1, T minus 2, T minus 3 up to last one. And I will vary from 1 to 1. This is the number of states. In this case also, the complexity is order of n square t. Here also, the complexity will be at the order of n square t. I think we can take for 10 minutes more, then after that we can give 10 minutes break. Believe it to be okay? Hello?
Yes, it is fine. It will be okay. No problem.
After 10 minutes we can give break. Otherwise, students will get, participants will get bored.
Yeah, we can have an interaction session. What we can do right now, we can see there are 3 questions in the chat box. So we can.
Okay. So now we'll go for questions and answers. Okay, sir?
Yeah.
After
So
that,
can you see the chat box?
I will see that.
Yeah. Or should I read for you?
Or you can ask, and then the participants can directly ask the questions.
Yeah, that is also fine.
Okay.
Prashant has posted a question. May I request Prashant to please, or I can read it out.
Okay, please read.
He's asking that how to decide whether we have to use continuous HMM or discrete HMM.
Okay.
On what basis we should decide?
Okay. Actually, it depends on the problem. What problem you are taking? Okay. Such as we have taken this urn and ball model. Okay. This is the example of discrete HMM. We are taking one ball, then we are replacing. So it depends on specific problem to problem where we have used continuous and discrete HMM. Okay. Any other question?
Yeah. Next question is from Rohan Nisa. Question is, for speech recognition or speaker recognition, can we feed raw speech signal to deep neural network like CNN, RNN, LSTM, and other variants directly without applying the feature extraction techniques like LPC, MFCC, and so on? She wants to say whether we can apply DNN without using features of MFCC, LPCC.
Now, okay, I got the question. Now, in machine learning and deep learning, we can use the raw data and then we can see the results. Previously, when you to perform the basic technology, that feature extraction from raw data, then we do the pre-processing on raw data, remove the noise, or remove some headphone disturbances, all those things were taking place. But now, up to some extent, by using the machine learning techniques and deep learning, especially in deep learning, we can use the raw data and then we can get the results. That is possible now. And initially, actually, this speech recognition was taking place mostly on MATLAB. Then it was switched on to some specific tools like STK, Toolkit, and other toolkits called the. Now, presently, what of the work is taking place, that is using Python and the latest tools. So now the system of working is totally changed from MATLAB to the toolkits, then toolkits to Python. So that is possible.
Yeah, so next question is from Danish Raza, a scholar of computer science. He's asking, how can we go for the development or from where to start for speech recognition of any regional language for which ASR is not available? Any points should we keep in consideration before starting the process?
Yes. Now, actually, there are in India, see, our country is a very beautiful country. We have unity in diversity. We are Indian. But if we go to UP, the accent is different. The language is Hindi. Basically, in UP will speak Hindi. If we go to Kerala, the language is Malayalam. If you go to Tamil Nadu, the language is Tamil. So his question is that, what is the question? Can you repeat once again?
Sure, sir,
Hello?
sure. I'm repeating. How can we go for the development or from where to start for speech recognition of any regional language
Correct.
for
Okay.
which ASR is
Understood. Now, for any regional languages, suppose that you want to start for the Urdu language. Okay. You should have a proper database in that particular language. In many of the languages, the freely database is available. I will provide the website. I will, I think Umar sir can also tell. The database is available free of cost. Even if we developed one project, in that project, the language, the database in Hindi, Jharkhandi, Hindi spoken in Bihar, then in Bangla, then it is in Kannada, then it is in Malayalam, and Udiya. So these language database is available. That is available for public use freely now. If there are some language are in danger, that means those languages are spoken only by, let us see, by 5,000 people, 4,000 people in a specific region in a country. Then you should go there, you should prepare the specific database for that language, because for any automatic speech recognition system or speech recognition system, first of all, the proper database should be available. So many databases are available, but still some of the regional language database is not available. So you have to prepare first step is database. And proper database preparation, people think it is very easy task, but it is not easy. That is difficult most. Because feature extraction techniques, you have the programs in Python, in MATLAB. You have the system already developed. You have to give the input of that database. But what is not available? That regional language database is not available. So that database has to be prepared if you want to work for particular regional language. Then only you can build up automatic speech recognition system. And some of the projects have been done on this, that development of endangered languages databases. One project is going on at NIT Meghalaya, I think. NIT Mizoram and NIT Meghalaya on this language only. I visited there. They are collecting the database for endangered languages in that region. And then they will develop the automatic speech recognition system. I think it is clear now.
Yeah, thank you, sir. And this next question, the participant is asking, is HMM also helpful in text to speech conversion?
Text to speech conversion.
Yeah, hidden Markov model can be used for text to speech conversion.
Okay. Now, see, I will tell you, there can be different methods here. Text means if you take the image of the text, okay? So image of the word will be different from one word to one word or from one phoneme to one phoneme. That image you give as input to be converted into speech. So definitely we can use the hidden Markov model there, because hidden Markov model is a classifier. It will classify different images into different groups depending on the number of inputs and how many outputs you want. So it can be used.
Okay. One more small query here. I think it's a statement or Miss Kajal Singh. She's asking, speech recognition can improve in implementing of drone or in robotics field. Whether it's a question or some comment.
Okay, I have understood. Now, I think she want to ask that how speech recognition technology is used in maintaining of the robotics or in the drones, correct? Now here, presently, the speech signal operated drones are available. And not drones, that speech operated robotics are available in different countries. Though robots can be used in danger places where the human being cannot work, or it is very, very high danger or high risk for a human person to work. So based on speech signal commands, the robots can perform the human task very easily and with efficiently. One thing. Second thing, they are not far away. These robots will be used in wars also in place of human beings, which will be operated by speech commands or by some other techniques with the help of wireless technologies. So technology is already in the development, and this is a one very good research area for the newcomers. Now in speech, automatic speech recognition technology, many things have happened. Many people have implemented HMM, GMM, speaker recognition, speech recognition, speech to text. So the scope is still lying in the field of robots, development of speech operated robots, and the scope lies development of IoT circuits integrated with speech commands for the welfare of the old people and disabled people, or not only for old and disabled people, for you yourself. Suppose that you are studying at night up to 12 o'clock or 1 o'clock. You are in one room. Light is on in another room. You want to switch off. You take the mobile from there only, you can switch off that light. So that provides the comfort for disabled and people, or for old age people. Definitely very, very useful, but it is useful for normal people also. So many people are working in that. In IoT, people have used Raspberry board with interface with the speech, a small speech recognition system that it will convert speech signal into the commands, and then it will be operated. Practically, I have seen this at one college. Students have developed a small project. They are operating only by using 4 LEDs. They're giving speech LED on, LED off, LED number 1 on, LED number 2 on, LED number 3. 4 LEDs they were operating by using speech signals on, by using only on Arduino ID. I think in your Aligarh Muslim University also, some IoT lab will be there and some of the students will be working. So these small projects they develop, then they can go for advanced work. And many papers are also available on these two technologies. So definitely this speech have a lot of scope for various researchers. Only they have to use our basic fundamentals of speech recognition techniques for the applications oriented in robots or in integrated circuit of IoT and speech. And other fields are also available. Voice activity system, voice-based system. Lot many examples in the starting I've explained around 8 to 10 fields. So I think her question she will be clear from her question, correct? What she wanted to ask.
Yes, thank you.
Yes, sir.
Yeah. So there's one more small query or question from a participant. Can you suggest some tool for finding the audio amplitude or audio power in order to identify audio events?
You want to have
Find
some
the audio
tool
power, I think. She's asking
Correct.
audio power.
to measure the audio power and audio tools.
Yeah.
Okay, still I have not come across this, but I will see and give you reply. Ask the candidate to write me the mail. I'll reply that question. Okay.
Yes, yes. Thank you, sir. So there's one more question posted just now. Is there any research performed on developing ASR system for animals helpful in human interaction with animals? Very good question. So is there any research performed on developing ASR system for animals helpful in human interaction with animals?
Yes, actually, not only total human interaction with the animals, but one research scholar have worked at Kalinga Institute of Technology, interaction of the birds. He has observed the behavior of the birds with their sound That means they have collected the database of the words in Odisha at one place where many words are available at different instants. And then they observe the behavior of the birds, how the birds behave at different times, what kind of sound they're making. That means how they're communicating among themselves at particular event when they're in the danger or when they are free. So one student has worked in that field, but not interact with the human being. I have not come across, but definitely some people will be doing the work in this field.
Yeah, thank you, sir. And now, actually, this session is around, in total minutes which have been allocated to us is 140 minutes, 150 minutes. So we have not given break. So we can, I think we can continue the session, and maybe by 9:15 or 9:10 we can end, or 9:15.
Okay. So what I will do, for 10 minutes I will continue, then we'll give 5-minute break. Okay?
Yeah, thank you.
And then I will take one numerical problem. So students will have that. I have explained the forward algorithm and Viterbi algorithm I not explained, and other direct solution. But with theory itself, the student may not follow the exactly. But once I'll take that example, it will be clear how we use Viterbi algorithm to find the optimal state sequence, how we calculate the probability of observation sequence for a given lambda by using forward procedure or a backward procedure. So I will take for 10 minutes this session, and then I will give 5-minute break. Then I switch on with the tab. In that tab, I will explain that problem. I think that will be better, correct?
Yeah. That's
so I will continue for 10 minutes. Okay. Yeah. Now I will share PPT. All of you can see the PPT now?
Yeah, participants, please acknowledge.
Yes, sir.
You can see the PPT. So I will not explain all the slides, but I will explain some of the slides from that. Then I'll give 10 minutes break, and then I'll explain practical example. Now this is Viterbi algorithm decoding by using Viterbi algorithm. Here in Viterbi algorithm, see state sequence maximize. What we do here, we'll calculate probability of observation by taking the maximum value. But the forward algorithm, we add the values. We take the summation. Here we don't add. We take the maximum value. That is the difference between two. These forward algorithms and Viterbi algorithms is almost all same except this state. Here you see, we'll select the maximum value from this. Okay. Now, so this I will explain the help of numerical problem. Then it will be very easy. Third problem is, how do we adjust the model parameters lambda, AV pi, to maximize probability of observation for a given lambda? So third problem is maximization of adjust the model parameters of lambda to maximize the probability of observation sequence for a given lambda. Here we use Wormbench algorithm. After that, HMM and ASR. In automatic speech recognition system, HMM is used for many purposes. HMM can be used to classify feature sequences to known classes. Make a HMM to each class. By determining the probability of sequence to the HMM, we can decide which HMM could most probably generate the sequence. Now, I will take example of a isolated word recognition or limited digits recognition. One diagram I have. Then HMM can be used for monophone acoustic model, approximately equal to 50 HMM. HMM can be used for triphone acoustic model. Those you are working in speech, actually in 2 hours, everything cannot be explained. But triphone acoustic models, HMM for each 3 phone sequence, that is 50 to the power 3 to becomes here. Here it is only around 50, it becomes 50 to the power 3 once it becomes triphone. Okay. Each triphone has 3 states. Now, there are types of HMM. Bucky's model. Bucky's model here, left to right model. We'll go from left to right. You see here, from step 1, we can go to step 2, 3, 4. So A11, A12, A13, and A14 is available. Now, step 2, A21 is not available. We cannot go back. So this is the state transition matrix for this model. Another model we have erodic model. Erodic model means I have explained you the weather model, that is rainy, sunny, and rain, sunny, and cloudy. So here in that model, we can go from any state to any state. That means all these state transition probabilities, A11 or A41 or A24, every state transition probability will be positive only in this type of model. In other types of models, some of the state transition probability will be zero, means model cannot go from that state to another state. Okay, so strongly connected directed paths are positive probability. Every path will have the positive probability here in ergodic model. That is, the Bayes model is also the same model. We have all 9 probabilities there. Left-right HMM can only transition to higher states or stay in the same state. See, from S1 we can go to S2, S2 to S3, S3 to S4, or we can stay in the same state. That means here you see in between only the state transition matrix exists. Here it is also 0, at this side also it is 0. Okay, so then this is one isolated word recognition system. I'll give a rough idea for this. I will not go in detail. Okay. Now we are going to, let us take, I am taking an example of n words. We are going to recognize n word using hidden Markov model. So first of all, here the speech signal is available at the input. We will calculate the features. Here we have calculated statistical features. Okay. Now those features will be used for training purpose. In HM model, training nothing but we'll find out the models for the respective words. We are having n words. That means first we'll calculate lambda 1 for the word 1, lambda 2 for word 2, lambda 3 for word 3, and lambda n for word n. So if we want to go for word-based recognition using HMM, we have to create n models, one model for each word. Okay, during the training phase. Then we'll go for testing phase. We'll calculate the same features here, and all those same features will be given as input here, and maximum likelihood ratio will be calculated at this point. Based on maximum likelihood ratio, it will recognize this is word number 2 or word number 3 or word number n. Okay, this is the basic concept of HMM. We create HMM model, either phonic based HMM or word based HMM, whatever type of speech recognition system you are developing. Based on that, we use the HMM. HMM is not only used in speech recognition system, it is used in thousands of applications, and thousands of papers are available on hidden Markov model. It is not limited only to this. Then these are the references. Now we can take 5-minute break. Immediately after 5 minutes, I will start on second device. I will connect on my second device and I will explain one example, beautiful example. With the help of that example, I will try to explain forward algorithm and Viterbi algorithm, so the student can understand easily what is forward algorithm, what is Viterbi algorithm, how can we practically apply that, how it can be done. It is done practically inside the system. Because once we work or researchers work in any of the tool, already the syntax is available, you give the command, but we are not able to know how it is happening. So I want to make a feel with the help of that example, what is happening in forward algorithm, what probability we are calculating, how we are maximizing the path sequence. All those things I will explain with the help of that example. So after 5 minutes exactly meet 20:43. So 20:50 I will start after 7 minutes. Is it okay, sir? Hello?
Yes, that is fine, sir. That's okay.
Okay. So after 20:44, after 5 minutes, I will be available online. Okay.
Okay, fine.
Okay, sir. Thank you. I am leaving this. I will join back on my tab.
Yes, yes. So participants can remain online. And
I will join on tab after 5 minutes. Okay,
Yeah,
sir?
fine, sir. We will be taking 5 minutes break. We are online. We are
Okay,
not
sir.
disconnecting, but you can
Okay,
join
sir. Okay, sir.
after 5 minutes. No issues.
Okay, sir.
Okay, sir.
No, no, sir, it's all out and the motor.
Good evening, all. Can you hear me now?
Yeah, good evening, sir. We can hear you, sir.
Okay, should I
Good evening,
start the
sir. We
session?
can hear you, sir.
Should I start now,
Yes, sir.
Okay,
Sure,
sir.
sir.
or should we wait for 1 minute more? Somebody may be coming.
Maybe we can start. We have already told.
Okay.
If you wish, you can take 1 minute more break. No issue.
No. I will start now.
Okay.
Can you see my screen now? Note title.
Yes, sir.
I will write something. Okay. Now we are going to use. First, I will write observation. Okay. So I will use the So I will explain forward algorithm. Okay. In the forward algorithm, let us see, we have been given observation. Observations are given to us. Normal, cold, and digi. I've been given one observation sequence, normal, cold, and digi. Okay. Normal means person is normal. Cold means he have some cough and cold. Digi means he is feeling uneasy, some like that. Now, apart from this observation sequence, we have state transition matrix and emission matrix. And before that, here we have number of states n is equal to 2. Okay, I will tell you what are those states. Those two states are healthy and fever. Those two states are, first state is healthy and second is fever. Okay, the person can be healed, healthy, or he may have fever. There are only two states. I am considering this example. Okay, now I have state transition matrix and emission matrix. Emission matrix indicates the probability of the observation sequence. So I'll combine both the matrices. I will write down this is health, HEALTH, and I will write down here fever, FEVER. So I have taken one is healthy. One I am taking healthy and another is fever. I am taking these two states. Okay. This side I will take here. Healthy, I will take here H. I will indicate healthy by H here. I indicate fever by F here. Okay. So when a person is healthy and it remains healthy, the probability of that is 0.7. When a person is healthy and he gets fever, it is 0.3. When person is having fever and he is healthy, probability is 0.4. When person is fever, again he has fever, it is 0.6. This is called your state transition matrix. Okay. There are two states. One is healthy, another is fever. I have written those two states here in short. H means for healthy, F means for fever. We have three observation sequence. That is, I have here normal, then cold, then dizzy. This is called your emission matrix. So this matrix I will call it emission matrix. Emission matrix means observation symbol probabilities. So I've combined both the matrix together. This first half is the transition matrix, state transition matrix, and second half is your emission matrix. All of you can see my slide? Hello?
Yes, sir. It is.
Yes, sir.
It is
Okay.
visible.
Yes, sir.
So now here, once person is healthy, he will be normal. But the probability of that is 0.5. When the person is healthy, he will have cold. The probability is 0.4. Person is healthy, he will feel dizzy. The probability is 0.1. Like that, I'll fill all the probability here. And the person is having fever, probability is normal 0.1. When the person is having fever, he may be felt in cold 0.3, and here it is 0.6. So what is given to us? We have been given observation sequence, that is normal, cold, and dizzy. So, and we are given two states. One is healthy, one is fever. So for all those two states, I have state transition matrix and emission matrix. Now, I will go further. I will see these things. Okay. Okay. Now, we'll go. We will start here. We will start okay. So we will start at this point. After starting, see, we can go to health. I will write here health H. Next state, again, we may go to health H. Next state, again, we may go to health. Healthy, that is H. State is healthy, all three. Another can be, from start, we can go to fever. We can go to again fever. he can go to again fever. Okay. Now here I will mark this. I'll mark by 1. This I'll mark by 2. This I'll mark by 3. Okay. This I'll mark by 4. This I'll mark by 6. This I'll mark by 8. Here I'll mark by 7. I'll change the color now and we'll mark this one by 3, 1, 2, 3, 4, 5. Let us see 5. And this one I'll mark by 9. Okay. So for this, from one state, when you go to another state, I give a number. So once I calculate the probability along that path, I will write the number here. That's why I made it easy. Now what is known to us? What sequence is given to us? We have been given normal. That means here we have been given normal. NOR. Okay. I'll write normal here. So at this place, first observation sequence is normal. Second is your cold. Third is digi. This is given our observation sequence. Means in first state, normal. Second state, cold. Third state is digi. Now, I calculate the probability for path 1. That is at node. I will give the node number also here. Here I will give the node at this point A. Here I will give B. Here I will give C. Here I will give D. Here I will give E. And here I will give F. I have denoted by them F. So at A, the probability of path 1 is, by the start probability of health, we are going to health. So start probability of that, okay, that I have not written. Okay, I'll write that also. Here, start probability pi we have, I'll write pi here. I have pi is equal to 0.6.4. This is for healthy state and this is for fever. Now here, from at starting by the initial state probability for healthy, it is 0.6. So I'll take 0.6 multiplied by. Now, from healthy, we should be normal. So you see healthy here and normal is here. So healthy and normal is 0.5. So it is 0.5. So this is 0.30. Correct? That means at A, I am getting 0.30. Now I'll calculate at B. At B, I'll calculate for path number 2. I have denoted this path by 2. So start probability for the fever is 0.4. I have written here 0.4. This one I have given the state transition probability here. Okay. This is pi. N2. Now we are at this point, node V, where the state is fever. And it should be normal. So you see fever and then it should be normal. Normal means 0.1. So we'll multiply by 0.1. So it will be 0.04. I will write down those values. So this is 0.30. B is at 0.04. Now I'll go at C. At C, there are two branches, number 3 and number 5. So I'll calculate for 3. So for 3, we'll starting probability is 0.3 into. It is going from healthy to healthy. So healthy to healthy, the probability is 0.7. Then in second stage, a second observation is cold. So healthy to cold is 0.4. So I am getting this equal to 0.0064. All of you can see my screen? Hello?
Yes, sir.
Hello?
Your screen is visible to us.
Okay.
Yes, sir. Your screen visible to us.
Okay. Then so this branch 3, I have calculated here the probability 0.0064 I'm getting. Okay. Now this 5 path is also going to node C. So I'll calculate for 5. 5 means starting probability is F at node B, that is 0.04. We are going from fever to healthy. That is fever to healthy we are going. Fever to healthy is 0.4. Then at this stage it is cold. So from health we are going to cold. So healthy and it is cold 0.4, again 0.4. So this is equal to at number 5. 0.4, 0.4, 0.4. This is equal to 0.0064. But this top probability is 0.7, 0.3, 21 into 4, 84. This is 84. Okay, so this is 0.084. I'll rub it and write again. We have done mistake here. You multiply this 0.3 into 0.7 into 0.4. 7 to 4, 28 into 3. That is 84. Correct. This is your 84. And here 1, 2, 3. So 0.084. So at C, now what we'll do in forward algorithms, you should have seen we will take addition. We will sum both this. After summation of both this, I am going to get 0.0904. In forward algorithm, summation of all the probability taking place. We are taking summation if you remember that formula. So at C, the value is now 0.0904. Similarly, I'll calculate at D. Now we'll come to D. This is the D. At D, 3 and 4. 4 is coming. So we'll calculate first for 4. 4 is equal to 0.3 is the probability at this point. We are coming to this point. That we are coming from healthy to fever. From healthy to fever. 0.3, again 0.3. Then we are in the second state and it is cold. So fever to cold. This is fever and this is cold. So again 0.3. So this is 0.027. Okay. Then at number D, that node D, one branch is 4 and the branch is 6. So we'll calculate for 6 also. This for 6 also we'll calculate. For 6, here the probability is 0.04. Into we are going from fever to fever. Fever to fever, 0.6. Now at the stage 2, the observation is cold. So fever and cold. So this is fever and this is cold. So 0.3. So this becomes 0.0072. Now we'll add this both again. After adding this both again, I'm getting 0.0342. I'll calculate one more. Now E also I'll calculate at node E. Or let us calculate node E. Node E, we have 7. The path number 7, denoted by this. So 7 is equal to the probability here at node C I am having 0.0904 multiplied by health to health. That is healthy to healthy is going. So 0.7. Then in third stage, the observation DG. The person is healthy, he is feeling dizzy. That means this. So if the person is healthy, he is feeling dizzy, that is 0.1. So here we get 0.06328. Then another branch is going 9 here at node 9. 9 is going from here. See, this is a 9 is going at this node E. So here the probability of D, what you got at D? D will got point, D will got is equal to 0.0342. So 0.0342 into, we are going from D to E. So this is from fever to health. So fever to healthy we are going. So fever is this and healthy is this. Okay. Fever to healthy. So 0.4. 0.4 into. Now we are at this stage. Fever. When fever and it is DG. So fever and DG 0.6. This is fever and this is DG 0.6. So I'm going to get 9. We are at 9. 9 means we once again will see. This is the 9. Here the probability is 0.0342. Okay. 0.0342 multiplied by this branch state transition probability of this. That means person is having fever and is going to be healthy. So he is having fever, is going to be healthy, that is 0.4. So 0.4 we are written. Then the person reaches at this node E, he is healthy. And after that he is feeling dizzy. So he is healthy, he is feeling dizzy, that is 0.1, not 0.6. So this I am going to get equal to 0.001368. Again we'll add this both. We'll add this both and we are getting here the value is 0.007696. So this is at E. So at E, the value I'm getting 0.0076 I'll write. Okay. Similarly, I'll calculate the value at F. For F, I will not calculate here. At F, I'm getting two values. For 8, I'm getting the value here 0.016272. And for 10, I'm getting the value 0.012312. You can calculate a similar way. So now we'll add these two values. After adding, we're getting 0.0285. So I write at point F. At point F, what value I'm getting? Here I'm getting 0.0285. So I have calculated the values along all the paths. Now, listen carefully. Our problem is observation is given normal, cold, and dizzy. We have to find the optimal state sequence corresponding to this, or the probability for the optimal state sequence. Okay. In forward algorithms, what we'll do, we will add the probability at one node, how many values are coming, we'll add all that. So in this diagram, I have added that. Now we start from the starting, we are starting. So from starting, either we can go to healthy or we can go to fever. Now out of these two, which probability is higher? Here it is 0.30, here it is 0.04. I want from some candidate which is higher. Hello?
Sir,
I want which is higher. At point A, the probability is 0.30. At B, it is 0.04. Which is higher?
0.30.
0.30. Very good. That means out of these two, this becomes our optimal path sequence. Okay. Now from here, either we can go to node C or we can come to node D. Okay. Now out of these two, there it is 0.0904, here it is 0.0345342. So definitely at C, 0.0904 is highest. That probability is higher. So from here, we'll go along this path. Correct. Now from here again, we can go to two paths. Either we can go to E or we can come to F. Okay. Now E and F we can come. If you go, this probability 0.0076, here this probability 0.0285. So definitely 0.0285 is higher. That means we'll come along this path. All of you understood this tracing of the path, how we have gone from starting to the end. We have calculated. I will explain, then I'll ask. We have been given the state transition matrix. This is the state transition matrix here. This is the state transition matrix, only this one, okay? It's given to us. And this is your emission matrix given this side here, okay? Now, the observation sequence is normal, cold, and DG. We have to find out the state sequence corresponding to this observation sequence. That is our problem. So we have drawn the state diagram. Now there are only two states. One is healthy, another is fever. So here H I have written means healthy, healthy, healthy. F I have written fever, fever, fever. We are starting from here. So here we use the initial state probability in those two branches. That is path number 1 and path number 2. Here we use the state transition probability in between. At the end, we will have the emission probabilities. So this emission probability, after using state transition probability, we have to multiply by the emission probability. We will see these states, normal, cold, and DG. So I have calculated for all the path sequences the values. At C, I am getting two branches. One is from A to C, another from B to C. Out of these two, I am adding that. So in forward algorithms, we add all the probabilities at respective nodes. Then I have written those probabilities here, 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 and here, and here, and here. Now we'll decide based on maximum probabilities. This is a statistical model. A statistical model means which use the static parameters for prediction of something. Here the statistical parameters, we are going for probability. Okay. Out of that, we are using three types of probabilities. One is initial state, then another is state transition probability, and last one is emission matrix or emission probabilities. So now from start, if you go to node A, we get 0.30. We go to node B, we get 0.04. So out of these, the probability of node A is 0.30. That means system will go to healthy state. Now from this healthy state, depending on the second observation is cold. You see, person is healthy and that is corresponding to normal. That is correct. Person healthy means it will be normal. Then from here, we'll see node C and node D. Node C, we have 0.0904. Node D, we have 0.0342. Out of the two, the probability is higher at node C. That is 0.0904. So again, the system will go from healthy to healthy. Now, next two steps, we are at this point. Either we go to healthy or you can go healthy to fever, depending on the state. Then healthy to healthy, then come to this point. Here, the probability as per the forward procedure is 0.0285. The probability here is 0.0076. So 0.0076 much less than 0.0285. So this probability is highest. That means this is highest. So I will follow this path as per the forward algorithms. Okay. So now what is the solution? In solution, I will get state. So output is, okay, I will, so what is our output now? What is our output? I will take another color, wait. So our output is, see, first we have gone to healthy state. So our first output is healthy. HEALTHY as per the probability. Then again we are going to healthy. So next is also healthy state. Then from healthy, we are going to fever. So next step is fever. F-E-V-E-R. So this is the output what we received by using forward algorithm based on probability. That is healthy, and fever. And what was our input? Our input was normal, cold, and dizzy. Our input was normal, cold, and dizzy. Now we'll match these two. Once a person is normal, that means he is healthy, it is correct. Prediction is correct. Person may have the cold. So he may be healthy or fever. So little cold means he will be healthy. He is considered as healthy, depending on the probability. Third observation is dizzy. He is not feeling well, he is getting vomiting or something, he is feeling dizziness. That means he is having fever. That means the predicted output is matching with our observation output once we use the forward algorithms. Okay. Now you can ask me the doubt about this, how I solved. Anybody is having doubt, I will scan one paper, I will solve this problem on one paper, I will mail to Professor Wajid. He will give to you that solution also, okay, on one paper. Because you may not understand everything on that paper, I made it very clear.
Yeah, sure. I will share with the participants.
So that this problem and Viterbi algorithm problem also, both I solved. That tomorrow I will mail you, so that you can give to participants. Okay.
Yeah.
Now,
So
anybody having any doubt, I have taken forward algorithms. With that forward algorithms, what is the forward algorithm? We have to calculate the probability of the observation sequence for a given lambda. The observation sequence is normal, cold, and dizzy. Based on probability, that means he got highest probability corresponding to normal for healthy. Corresponding to cold, he got higher probability for healthy. Corresponding to dizziness, he got for fever. Okay. So that is the probability he got. Okay. Now, so our input is observation sequence normal, cold, and dizzy. We have been given the state transition matrix, emission matrix, and we have predicted output is healthy, and fever. If you don't have any doubt, I will explain Viterbi algorithm only in this diagram. Should I go for that now?
yeah. Actually, we can conclude by 9:30. So we have 7 minutes for that.
Okay, no problem. So within 2 minutes, I will explain that. Don't worry. Wait. Within 2 minutes, I will explain forward Viterbi algorithm here only. I will take only 2 minutes.
Yeah, sure, sir.
I will take 2 minutes. Okay.
Okay.
So now I will delete some of the parts from here. We'll go for concept of Viterbi. Now I will tell you now all of you pay attention. The most important difference between forward algorithms and the Viterbi algorithm is, in forward algorithm, we will add the probabilities. In Viterbi algorithm, we will take the maximum values out of available values. So here, in Viterbi algorithm, at point C, the maximum is 0.084. So I will take 0.084 here. 0.084. At D, I will take maximum value is 0.027. At E, the maximum value is 0.0063. 0.0063. At F, the maximum value is 0.016. 0.016. Now, once again, I will go for the optimal state sequence. What you want is optimal state sequence. Now, you see the probability will start from here. Out of this node A and B, the probability maximum here 0.3. So we'll go here only. Out of C and D again, we have taken maximum values. Again, the probability at node C itself is 0.084. Here is 0.027. That will go here. At H, we can go two directions, either H2H or H2F. Here probability is 0.016, here probability is 0.0063, so probability is higher here. That means this is our optimal state sequence. So our optimal state sequence, in terms of output, we can write down optimal state sequence here. Here, in place of output, I can write down optimal state sequence. That means first is healthy based on probability, second is healthy based on probability, third is fever here. So healthy fever. I got the same value as we got in the forward algorithm. Now somebody will ask why we got the same values. In forward algorithm, we are calculating the probabilities. In Viterbi algorithm, we are finding the state sequence. This is the optimal state sequence for this problem. Healthy, and fever. There, as per the probability, we predict that these are the states that are having highest probabilities. So here I'll end my session because we'll wind up. So I've not shared. Okay, so Professor Wajid, you can conclude now from my side, and if time permits, you can have one or two questions. Otherwise, let them give my mail. Let them write the questions. I'll answer them, and they can interact on my phone number also.
Sure, sir. Sure.
Okay.
So, participants, any question? If you have any,
whatever they feel good.
Yeah, I think they have asked many questions in the previous session.
Okay, but still they can post in my mail. You give them my mail ID. If anybody want to interact with me, they can interact with me on mail. Okay, no problem.
Yes.
So thank you everyone for joining my session. I have taken many things. I try to take many things. I have taken this example so that it becomes easy to understand this forward algorithm, Viterbi algorithm. And this notes also I'll share with Professor Wajid. He will share with you PDF. Okay. Thank you, one and all.
Thank you so much, sir.
Okay, thank you, Professor Mahesh. It was a nice talk, and in detail, what you have done is the analysis part where you have done the calculation. This was very, very important, so that participants over here would actually get the insight what is actually happening in the hidden Markov's model and how do we actually implement using forward and backward algorithm. And I hope that things would be more clear once you send those write-up, and then it is being shared by Dr. Wajid with the participants. So with this, I would like to thank you, and I would like to thank the participants also to be patient, and they have interacted with this with a resource person, and I am sure that they would have got a lot of insight in the speech recognition or hidden Markov's model, how it is being used for the speech recognition application. Because we are having a interaction which is remotely online, so I would just like to have a more virtual memento for Professor Mahesh Chandra and thank him for the nice presentation, the time that he has taken out from his busy schedule, because the entire day in the department, and then again speaking for 2.5 hours or 3 hours roughly in the evening also, being in between the dinner time, it is a tough call for the participants as well as for the speaker also. So I would like to thank you for taking out time, and I am sure that if there are questions that can be emailed to you, you will respond to the participants and clarify their doubts.
Thank you, sir.
Thank you very much.
Thank you, sir. Thank you all participants. I am
Thank
so
you.
privileged, sir, that I will talk at AMU Aligarh, and thank you very much.
No, sure, we will have more interactions in future with you.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you, sir. So for participants, I'm just sharing the attendance link. Please mark your attendance if you have not. I have just so thank you, sir.
Okay, sir.
Yes, sir. We can leave the session now, sir.
Okay.
Yeah.
Okay. Thank you very much. Thank you, one and all, and hope to see you tomorrow again. Same time. Have a nice time. Good night.